2.6, we're looking at a topic called related rates. In the last section, we looked at doing implicit differentiation, where we took derivatives of variables that may or may not be with respect to what we're taking with. For example, if we have x squared plus 3y equals 4, if we take the derivative of that with respect to x, we have a mixture of variables in here. But regardless, when we do that, we end up getting dy over dx, and what that tells us is the slope of an x versus y graph, which tells us how x is changing as compared to y. But that really doesn't tell us how fast over time it's changing. It just tells us if x changes a certain amount, how much is y changing. But there are times that we want to have a time factor involved. If we remember when we were looking at position versus time, and we said that if we take the derivative of a position versus time graph, it gives us velocity, then sometimes we want to know how fast something is changing over time, not just in comparison to another variable. So let's look at a couple of examples. Let's suppose that we have a square. Let's suppose that square starts out 2 centimeters by 2 centimeters. So to begin with, it has an area of 4 square centimeters. Now let's take that same square and let's increase its size by 1 centimeter on each side. So now it's 3 centimeters by 3 centimeters. So it has an area of 9 square centimeters. And we might say that that side changed, it grew 1 centimeter in a minute. So if we call this distance x, and of course that would be x, then the change in x we would refer to as dx dt. It's going to have how much it changed with respect to time. So we might say that it grew 1 centimeter in a minute. So notice what our change in area is. Let's suppose that same square grows for another minute. So now it goes from 3 to 4. So now if the side is 4 centimeters by 4 centimeters, now the area is 16 square centimeters. Notice in our first growth, we grew 5 square centimeters, and our next growth, we grew 7 square centimeters. So there's not always a direct relationship between how fast one variable is changing to the other. If one changes at a certain rate, the other one might not be increasing at a constant rate. So we need to know how our variables are related so we can make a prediction of, okay, if our square is a certain size, and if we know how fast one variable is changing, how fast is the other? So let's call our sides x. So the area of a square is x times x, or x squared. So if we want to know how fast they're changing over time, we're going to differentiate with respect to time, not with respect to x, because we don't want to look specifically at if x changes this amount, how much does the area change? We want to know if my side is growing at a certain speed, how fast is the area growing with respect to time? So if we take the derivative of a with respect to t is dA dt. If we take the derivative of x squared with respect to t, since our variables don't match, it's the chain rule, so bring the 2 down, x to the 1 less power times the derivative of the inside function with respect to t. So the derivative of x with respect to t is dx dt. So let's suppose that the sides are growing at a rate of 2 centimeters per minute. So if we're looking at how fast it's growing, that's dx dt. Let's see how fast the area is growing when x is 5 centimeters. We illustrated a moment ago that at different sizes, when we change from, let's say, 2 to 3 and 3 to 4, that size impacted how much the area changed. When it was larger, if I grow 1 centimeter, that's going to increase our area a lot more than if it's small and I increase 1 centimeter. So at the moment that our sides are 5 centimeters, then our area is changing at a rate of 2 times 5 times 2, or 20. That's an area. Our side is in centimeters, so our area is in square centimeters, and our time is in seconds. So at the exact moment that the sides are 5 centimeters, then our area is increasing 20 square centimeters per second. Or, I'm sorry, our unit time was minutes, not seconds. 20 square centimeters per minute. So let's look at another example. Let's suppose that we have a conveyor, and we have sand coming up that conveyor, and that sand is going to run off the end of the conveyor, and when it hits the ground, it's going to make a pile, and that pile is going to be a cone. It's going to be an inverted cone. The volume of an inverted cone is 1/3 pi r squared h. And let's suppose this is something that would be given to you. Let's suppose that the diameter is twice the height. So the diameter is from one side to the other. So this would be the radius. This would be the height. So if the diameter is twice the height, remember that the diameter is twice r. So in this case, the radius, oops, I crossed the wrong one. If I cancel the 2's out, the radius and the height are the same. Now, I believe the problem given for homework, the diameter was maybe 3 times the height, the diameter was 4 times the height, but that will give you a secondary equation that we can use to remove one of our variables here. Our volume is related to both the radius and the height, but we can use a secondary equation to remove one of those variables. Sometimes those are referred to as parameters. We want to know how fast the height is growing. How fast the height is growing. So a change in height, that's dh dt. Let's suppose that we're putting sand onto that pile at 50 cubic feet per minute. So that conveyor is running sand up there at a rate of 50 cubic feet per minute. That's a volume. So that's how fast the volume is changing for our cone. So if we're wanting to know how fast the height is changing, the only variable we really want on the right side here is height. We have radius and height, but if we could get rid of the radius, that would be great because we're not really interested in the radius. Well, we determined that for our scenario that the radius equals the height, so where we have a radius, we can change that to height. So that means in terms of height, the volume is 1/3 times pi times h cubed. So we always start out with what is an equation that relates our two variables that we're wanting to compare, our two rates that we're wanting to compare. And then we can take the derivative with respect to t. So take the derivative of the left side, that gives us dv dt. That means how fast the volume is changing over time. 1/3 times pi is a constant, and when we take the derivative of h cubed, we bring the 3 down, h to the 1 less power times the derivative of h. And with respect to t, that would be dh dt. Notice our 3's cancel. So dv over dt is pi h squared dh dt. We can solve for dh dt by dividing by pi and by h squared. So the rate at which the height is changing is equal to how fast the volume is changing over pi h squared. So if we think about that pile, when the pile is pretty small, if we put sand on it, the height is gonna change pretty quickly. It's not gonna be far to spread out. But when it's pretty tall, when you pour sand on it, sand's gonna be running down the sides, and it's gonna cover that whole surface. The height is not gonna change very much. So the rate at which the height is changing, that's related to how tall it is. At different heights, it's changing at different rates. So we want to know how fast the height is changing, specifically when our height is, let's say, when it's 5 feet tall. So that's going to be a given. So our rate that we're adding sand to the pile is 50. Pi is a constant. We're analyzing this when our height is 5 feet. So 50 over pi times 5 squared is 25. So 25 and 50 reduce. So dH dt is 2 over pi. We can get that as a decimal. 2 over pi. That's 0.637. 637. Our height was in feet, and our time is in minutes. So that tells us how many feet it's changing per minute at the moment that it's 5 feet tall. Now, if we want to put that into perspective, we can convert to inches. So if I have feet on top, I want feet on bottom. 12 inches is 1 foot. So if I multiply that by 12, that's about 7.6, it's roughly 7.6 inches per minute. So if we're pumping sand, rolling sand on top of our pile at 50 cubic feet per minute, then the height of the pile is getting taller by about 7.6 inches every minute. Of course, we said that as it gets taller, that rate is going to decrease because the sand has to spread out more. All right, let's look at one more situation, and let's look at a sliding ladder. Let's suppose we have a ladder that's leaned up against a building, and let's suppose it starts to slide. So let's suppose that the bottom of the ladder is sliding to the right at 2 feet per second. And let's suppose we have a 20-foot ladder that we're on. We're going to imagine that the ground and the building are perpendicular. We're going to call this distance x, this distance y. So x is from the base of the building to where the ladder touches the ground. Y is from where is the top of the ladder to the ground. So 2 feet per second, that's dx dt. That's how fast this distance is going to change, because as we slide that point to the right, that distance x is going to be growing. So dx dt, that's a positive 2 feet per second. So one question we could ask is, how fast is y changing? So A, we could say find dy dt. Notice if the bottom is sliding to the right, the top would be going down. So y would be getting smaller, so we would anticipate dy dt to be negative because y is decreasing. Now we're going to need a specific moment to analyze. So let's look at when x is 15 feet. So when the bottom of the ladder is 15 feet from the wall. All right, so we're wanting to compare dx dt and dy dt, so we need an equation that relates x and y. So x squared plus y squared equals the hypotenuse squared. That's an equation that relates our two variables. Now that we have an equation that relates our variables, we can find out how their rates are related. differentiate with respect to t, so we would get 2x times the derivative of x with respect to t, plus 2y times the derivative of y with respect to t, and the derivative of a constant is 0. If we want to find dy dt, then let's isolate dy dt, so move the x term to the other side. So how do we move it to the other side? We subtract it from both sides. So it would be gone on the left and would be negative on the other side. We want to get dy dt, so divide both sides by 2y. So we get that dy dt equals minus x dx dt over y. So to find out how fast y is changing over time, we need to know three things. We need to know x, that's given to us. We need to know dx dt, that's given to us. But we also need to know y, that's not given to us. But we have an equation that tells us how we can get y if we know x. So let me make a point real quickly before we find y. When we write our equation, even though we're looking specifically when x is 15, we're not going to put 15 in here before we take the derivative. If we put 15 in there and then we took the derivative, 15 would be a constant. And that would be saying that x is not ever changing. But that's not true. X is changing, so before we differentiate it, we have to leave that in as a variable. After we find how the rates are related, then we can put in a specific value for x, but until we get to that point, we need to leave it as a variable. Notice we did put 20 in for the hypotenuse and square it, because that value, no matter where the bottom is and where the top is, that value is constant. But x and y are changing as the ladder slides, so before we differentiate, we have to leave those as variables. So we need to get y. So x squared, we're looking when x is 15. So 15 squared plus y squared is 400. So 15 squared is 225. If we subtract that from both sides, we get 175. Take the square root, and we get that y is the square root of 175. That's not dy dt, that's just y. Technically, that the answer to that equation is plus and minus, but for our application, y is only going to be a positive value. It's not going to be a negative value. So now that we have all of our components of our equation, we can use that to find dy dt. So dy dt is minus x, x is 15, dx dt is 2, y is the square root of 175, and then we can calculate that. So 15 times 2 over the square root of 175, and then make that negative. I think I typed that wrong. Let's try that again. 15 times 2 over the square root of 175. So I get 3.46, which is negative. Let me double check one more time. So that's going to be 30 on top. The square root, not of 75. I can't type on this screen right now. Negative 30 on top divided by the square root of 175. Yeah, negative 2.27. I thought that was wrong. Negative 2.27. Y, that's the height, that's in feet, and our time component is seconds. So that's how fast the top of the ladder is sliding down the wall at the moment that the base is 15 feet from the wall. So let's answer another question about this picture. Let's still look at the specific moment when x is 15. dx dt is still going to be 2 feet per second. Our ladder is still 20 feet long. We found out that at this instance, dy dt is negative 2.27 feet per second, and we talked about why that's negative, because if this is sliding down, y is getting smaller. And we also said that y is the square root of 175. So what else could we possibly be interested in? Well, what about the area? If we look at the area of that triangle, we could look to see how fast that area is changing. Well, how do you calculate area of a triangle? 1/2 base times height. So that relates area to x and y. Now, since we were given initially that we're wanting to analyze when x is 15, it would be nice if we only had x on the right side of this equation. But to do that is going to be a little messy, because remember, the relationship between x and y is x squared plus y squared is 400. If we solve that for y and then replace y, that's going to be kind of messy. We're going to have a radical, we're going to have a product. We could do that, but if we have all the components we need doing it this way, then let's go for it. So if we're not sure, let's see what's going to happen if we differentiate this with respect to t. So if we take the derivative of a with respect to t, that's dA dt. On the right side, 1/2 is a constant, so leave it alone. And we have a product here. So if we think about this as u and v, it's the derivative of the first one times the second one plus the first one times the derivative of the second one. Now, since we're taking the derivative with respect to t, then when we took the derivative of x, that was dx dt, and when we take the derivative of y, that's dy dt. So u prime v, u v prime. Well, we know dx dt, that was given. We found y at the moment that x is 15. We were given x, and we also found dy dt at this moment. So if we want to know how fast the area is changing, we can just substitute those values in. So 2 times the square root of 175 plus 15 times negative 2.27. And then we can compute what that change in area is. So 2 times the square root of 175, that's this first part. And then we're going to add whatever we get when we do 15 times negative 2.27. I'm putting that in parentheses so it does that product before it adds it. So this is what we get on the inside of that parenthesis, and then we're going to multiply it by 1/2, and we'll get negative 3.796. Negative 3.796. Our lengths are in feet, so our area is in square feet, and our time is in seconds. So our area is getting smaller by about 3.796 square feet per second when our ladder is sliding down the wall at the instant that this distance is 15. Now let's answer another question. Same picture, same distances. Let's see how fast this angle is changing. Let's call this angle theta. This is still x, this is y, this is 20. Let's see how fast the angle is changing over time at the moment that x is 15 feet. So we need to begin by finding a relationship between theta and our triangle. So we are given something about x, so let's relate theta to x, and then 20 is a constant. So x is opposite of theta, 20 is the hypotenuse, so we could say that sine of theta is the opposite side over the hypotenuse. So this relates x to theta. Now we can take the derivative with respect to t, and that should give us how this rate, dx dt, how it's related to how fast theta is changing. Because as this slides down, this angle is going to be changing. So if we take the derivative of sine, that's cosine. But since our variables don't match, we also have to take the derivative of the inside. So this is the chain rule. The derivative of the outside is cosine times the derivative of the inside. The derivative of theta is d theta dt. We could rewrite x over 20 as 1 over 20 times x. So 1/20th is a constant. The derivative of x is dx dt. Now we're looking for d theta dt, so let's divide by cosine. So we have 1 over 20 times dx dt over cosine. Now we don't know what theta is at this moment. We could find it, but we don't necessarily have to know what theta is, because we know that cosine is adjacent over hypotenuse. So at the moment we're looking for, when x is 15, we know that y is the square root of 175. So at that moment, cosine of that angle is adjacent over 20, so root 175 over 20. So notice we didn't find a value for theta and take cosine of it. We just found out what cosine is for that triangle at that moment. Dx dt, we said earlier that's 2. Cosine at this moment is root 175 over 20. Instead of dividing by a fraction, we can multiply by the reciprocal. So the 20s would cancel. So the rate at which the angle is changing is 2 over 175. 2 over the square root of 175. So take 2 divided by the square root of 175, and that's about 0.151. Our angle is not in degrees, it's technically unitless, so that would be considered radians. Our time is in seconds. So that lets us know how fast that angle is changing over time. So all of these, whatever rate we're looking for, we need to write a formula that relates our variables, and then once we have how our variables are related, we take the derivative so that we can get how our rates are related. Notice we had this relationship between x and theta. Once we took the derivative, now we have a relationship that involves the rate of x and the rate of theta.